Welcome students to your favorite channel PRADIP classes as PSC, and today we are going to discuss with Gauss's law, and it is the application that is on spherical cell. Then you have to calculate electric field intensity due to a spherical cell. And students, if you are first in that particular class, then go back to the previous class and enjoy the concepts and then join again. Okay. So what is about Gauss's law? Here Mr. Electron are enclosed within a confined surface, then flux, the converging flux, all the flux generated by this electron, and this is equal to charge by epsilon naught. So the net flux through a closed surface is 1 by epsilon naught times net charge enclosed within the surface, and also we can explain as that is phi net. That is phi net is equal to closed integration of E dot ds, and this is equal to Q inside by epsilon naught. So you have to know that particular concepts that is related with Gauss's law. Okay, so net flux is equal to closed integration of electric field. Net flux is equal to closed integration of electric field, and this is equal to 1 by epsilon naught times net charge enclosed within the surface. And due to this electron, the flux equal to electron by epsilon naught. So it is so simple concept. And now we apply that particular concept, that is Gauss's law, on a spherical cell. So first of all, students, what is cell? What is cell? You have to know what is cell. So this is a cell. This is a cell. And this is also a cell with a layer. Okay, this is a cell with layer. So it is also a cell, but not thin cell. It is a cell, and this is a sphere. It is a sphere, solid sphere. So first one is a cell with thin cell, and the second one is a cell, and the next one is a solid sphere. So you can consider this is a soap bubble, and this is like football, and this is like ping pong ball. Okay, so these all the non-conducting materials, and for today's class the question is, so students, write down the question. What is the question? And calculate electric field intensity calculate electric field intensity due to a thin spherical cell, at thin spherical cell of radius capital R. Okay, at when at r is greater than r, at r is equal to r, and the c is r less than r. Okay, so write down the questions and explain again. So calculate electric field intensity due to a thin spherical shell of radius capital R. So the question is, this is a spherical shell, this is a spherical shell, okay, and this is the radius R. So if some charge is given to this shell, then all the charges distributed over the surface. Okay, so if a charge q amount of charge is given to the sphere, then charge density sigma equal to total charge by total surface. What is the surface area of a sphere? You can know that sigma equal to q by 4 pi r square. So this is, all the charges are uniformly distributed, and you have to calculate electric field intensity at some distance. That is, p is the distance, and this is small r. This is small r, and it is r distance apart. The observation point is r distance apart from the center. Okay. So this is the observation point, and you have to calculate a Gaussian surface. What is this Gaussian surface? It is an equipotential surface. Okay. So you can consider a Gaussian surface, a hypothetical surface, and you have to calculate that a flux is generated and penetrating that particular surface like that. Okay. So all the charges are on the surface of the thin spherical shell, and electric field lines are crossing that particular Gaussian surface. This is hypothetical. This is imaginary surface, and this surface is called Gaussian surface. Okay, so this is Gaussian surface, and the field lines generated due to this charge distribution can penetrate that particular Gaussian surface. So you can consider here a small area, that is the area vector, that is outward normal is along this direction. You have to take outward normal for that particular surface, and the electric field lines are directed along that particular direction. So if electric field is a function, then the electric field is a function of r vector, then r cap is acts along this direction, and since this is along the direction of n cap and r cap is 0 degree, so r cap dot n cap equal to a dot b equal to a b cos 0 degree, that is 1. That is 1, because from the rules of dot product, you know that a dot b equal to a b cos theta, but here there are two unit vectors, so the magnitude of the unit vector is 1. That is 1 into cos 0 degree, that is 1. Okay. So r cap dot n cap, and this is equal to 1. Now you can apply Gauss's theorem for that a small surface. So Gauss's theorem, d phi equal to E dot ds. From the definition of flux, we can write here as d phi equal to E dot ds, and here phi equal to eds, that is E vector dot ds vector, and this is integration, closed integration. Why you can take closed integration? For all the fluxes. So net flux equal to, so F net phi net, so phi net equal to closed integration of E dot ds, and this is the sign of integration, and when it is taken in a closed surface area, then you can say that this is closed surface integration of electric field. So electric field, E is a vector quantity, so E, and you can write a unit vector, then ds vector, and then this is ds, and here is also a unit vector, that is L cap. So this is a closed surface integration either of these. And then this is, you can write EDS, since r cap dot n cap is a unit vector, and since this is acts along that particular direction, so 1 into 1 cos theta, that is r cap dot r cap, and this is equal to 1. Okay, so the net flux equal to net flux through this surface. What is net flux? All the field lines crossing that particular surface is this number. So this is equation 1. Okay, and now you can apply Gauss's theorem. So applying Gauss's theorem, you can write, so applying Gauss's theorem, and here we can write applying Gauss's theorem or Gauss's law, applying Gauss's law, phi net equal to q, that is capital Q by epsilon naught. Here if you consider that this is the Gaussian surface, the net charge enclosed is capital Q, so flux phi net, and this is equal to Q by epsilon naught, and this is equation 2. So equation 1 is phi equal to closed integration of electric field, and the equation 2 is that is Gauss's law is phi net equal to Q by epsilon naught, and this is the definition of flux, and this is Gauss's theorem. So we can equalize this and this one, so we get closed integration E dot ds, and this is equal to E into ds, since n cap dot r cap, and this is equal to 1, so EDS equal to Q by epsilon naught. So EDS equal to Q by epsilon naught. Okay, so you can write here as sigma equal to Q by 4 pi r square, and the equation is, so this is EDS or E, and if we integrate that particular surface, then it is the radius is, since the radius is r, so the surface area is 4 pi r square. So closed integration of ds, since electric field is a constant value, here it is electric field is E, here also E, since all the points are on the Gaussian surface, possesses the same electrical field intensity. So closed integration ADS equal to Q by epsilon naught, you can, and the Q is sigma into 4 pi r square. So Q is sigma into 4 pi r square by epsilon naught, and you can cancelize this 4 pi and 4 pi. So E equal to sigma by epsilon naught into capital R square by small r square. So this is equation 3. Okay, so electric field where we can calculate, that is 1 when capital small r is greater than capital R, that is outside the sphere. So outside the sphere, then where R is greater than R, then electric field intensity at that point is sigma by epsilon naught r square by small r square. Now the question is that what is the electric field? What will be the electric field on the surface of the spherical cell? Then students, now think, if that observation point is at that point, that is small r, that is this point is shift at that particular point, then small r is equal to capital R. Okay, so just you have not applied that particular one, and just you can apply small r is equal to capital R. Okay, so the second part is what is the electric field on the surface? Where R equal to R, then you can write E on the sphere is equal to sigma by epsilon naught, and here small r, capital R square. In place of small r, you can write capital R square. So this is sigma by epsilon naught. So this is the point R is greater than R, and this is the point R is equal to R, and another point. What is the electric field R when R less than R? That is when the observation point is here. That is, this is the R. Then you can consider a Gaussian surface over within the spherical cell. You can consider a Gaussian surface within the spherical cell, and within the cell, what is the, now I ask you a question, students, what is the charge confined within that cell, within the Gaussian surface? Then you can say that there is no charge within this Gaussian surface, since all the charges are distributed over the spherical cell. So the charge confined within that Gaussian surface is 0. Then hence you can write the electric field is equal to 0. Since the charge is 0, then flux equal to 0 by something means 0, or electric field is 0. So if we calculate electric field due to a spherical cell outside the cell, then this is the expression, that is electric field is equal to sigma by epsilon naught. The electric field is sigma by epsilon naught R square by R square, and if it is on the surface, then electric field equal to sigma by epsilon naught, and inside the cell it is 0. So this is a vital point. Electric field inside a spherical cell is 0. So electric field inside it. Now write down the equations only. This equation, and this equation, and we can graphically show that particular variation of electric field with some distance. Okay. So plot a graph. The next one is plot a graph showing the variation of electric field versus small r due to a thin spherical cell. Then you can, if I take this is the r and this is the electric field, then, and this is a capital R, that is this is the radius of the cell. And then you can say that the inside that particular one, the electric field is 0. So the graph starts from that point. So this value is on the surface, that is sigma by epsilon naught, and then electric field is a function, that is electric field equal to sigma by epsilon naught, and this is capital R square by small r square. Okay. So electric field is inversely proportional to this one, since sigma epsilon naught and capital R is a constant. This value is constant. So electric field is inversely proportional to R square, and on the sphere it is sigma by epsilon, so it is a fixed value, and within the sphere, that is when small r is equal to r, then it is 0. So here it is 0, and the electric field is maximum value, and then it is decreases, and since it is a function, then you can say that this is 0 somewhere within the spherical cell, but where it is 0, then you don't touch here, because it means that electric field is somewhere here. But electric field is a function of r, and function of r cannot be 0 at some points. Okay, so it is decreasing in nature, so it is inversely proportional to r square, that is decreasing nature. And I think students, you have cleared these concepts, and you realize this one. So last of all, as I say, continue your study, and thank you for watching this video, and wait for the next one, and that is due to a spherical body. due to the spherical charge distribution, and it is a solid sphere and then shell with a thickness. Okay, and also consistently, and also you can watch AC VERMA series, that is the numerical king series, and the Irodov, that is a classic text series. Okay, thank you and continue your study.